In this video, I'll show you how to make your own USB 2.0 high-speed hub and how to incorporate USB hub ICs into your own projects. We'll look at the system overview, as well as dive into the schematic and PCB design. If you haven't already, it would really help me out if you subscribe to the channel. I see we have had about 134,000 unique viewers. I've got many different PCB design videos on my channel grouped in a playlist, as well as DSP, audio electronics, and many more videos to come, of course. In this video, I'll show you how to design your own USB hub, going through all the basics, looking at the block diagram, schematics, and then finally PCB design and what to watch out for. USB hubs, I'm sure you're very familiar with. They're devices that expand one single connector or one single USB interface into an array of several connectors or interfaces. So we can go from one host connector into, for example, 4 device connectors, so to speak. USB hubs come in various flavors. Commercially, you can get them for not very much money. Typically, you'll have some sort of host connection, which is a USB-A male connection, to, for example, 4 USB-A female connections, and they'll come in USB-C, various different standards, and so on. In this video, we're going to be looking at a USB 2.0 high-speed connection with 4 ports, and then one additional port which goes to a host. Not only is this useful for making a USB hub, if you want to try it and make one for yourself, it can of course be quite interesting, but a lot of times projects will require multiple USB connections. For example, a while ago I was working on an NVIDIA Xavier carrier board, and the particular system on chip only had one USB 2.0 connection. I had multiple different USB devices, so I needed to use one of these ICs, which we'll look at in this video, to expand this one port into several downstream ports, so to speak. One of my favorite ICs, and the one I actually used, is this USB 2514 by Microchip. Now these come in various flavors. You can get them a 2-port, 3-port, 4-port, and I believe even more, but we're going to be looking at the 4-port variant, which is indicated by this 4th digit over here. This is a USB 2 high-speed hub. It's very easy to configure, as we'll see, and I'll guide you through the design process. Thank you very much to Altium for sponsoring this video. I used Altium Designer to design this USB hub demo board, which we'll examine in this video. If you'd like to give Altium Designer a try for yourself, you can go to altium.com/YT/PhilsLab or follow the link in the description to get yourself an Altium Designer free trial. To make things a bit easier before we move on to the schematic, where we then add more detail, let's have a look at this USB hub system overview. And I've made a little block diagram. The centerpiece is, of course, our USB 2.0 high-speed hub, which is the Microchip USB 2514B. This requires a connection to a host, and this will be the data connection, the main data connection, which we then branch out to several slaves. For this, I quite like Micro B. I know USB-C is quite popular as well these days, and of course you're free to choose whatever you want. We're talking to a host via Micro B. We can plug in a cable, we have a differential data pair, and we also have a V-bus detect pin for this USB hub to tell the hub, okay, we've connected a host. To run this hub, we also need power, and instead of getting this from the Micro B connector, because we have quite large current consumption requirements, because we are using 4 slaves on the right-hand side, I'm also adding a DC barrel jack, and this will be nominally at 5 volts, and we need to supply about 2.5 amps maximum current. Then of course the USB hub typically works on 3.3 volts, so we need another regulator, and 5 volt to 3.3 volt. Because this regulator doesn't draw very much current, an LDO or low dropout linear regulator is perfectly fine. We don't really need to use a switching device. It simplifies our design considerably. On the other side of this USB hub, then of course we have all the device connections. So we want to have the host talk to several devices, so we need to branch out, in this case 4 times, so we have 4 times the same circuitry for 4 devices. Again, we have differential data pair connections going to a USB-A female, and USB-A female is pretty much the standard for device connections coming from a host. But we also have this load switch, which you see here. According to the USB standard, without negotiation for USB 2.0, we can draw about 150 milliamps. However, the device can negotiate with a host and then draw up to 500 milliamps, but not more. Therefore, we need a load switch which limits the current to the device after negotiation. So the load switch will clamp at a maximum of 500 milliamps at 5 volts, but it also has various signals to which it can talk to the USB hub with. One is the enable signal. So the USB hub after negotiation can say, okay, let's enable this load switch. Let's enable the 5 volts on this port. But the load switch can also talk to the USB hub, essentially by 1 GPIO, and this is an overcurrent or OC flag pin. So anytime there's an overcurrent problem, we want to let the USB hub know. All in all, it's actually a pretty simple connection. We have data and power. And the power is coming from our DC barrel jack, as we said before. And this circuitry is simply multiplied another 3 times. So we have 1, 2, 3, and 4 devices. That's almost all we need for our USB hub, but we also need some configuration as well as some sort of timing source for this USB hub. The timing source typically for these hubs is a 24 MHz crystal, even though you could also use a CMOS oscillator. The other part to this is either an EEPROM or what's known as strapping resistors connected to strapping pins of this USB hub. In essence, when this USB hub first boots up, it'll sample the EEPROM, or it'll sample the state of certain GPIOs, and then configure itself in different modes. This could be the amount of devices that are allowed to be connected. It could be if this is self-powered or if this is bus-powered. In our case, this is self-powered because we have an additional DC barrel jack, and so on. But it can also include VIDs and PIDs, so vendor IDs and product IDs, which are part of the USB 2 standard. But in our case, we want to make it just a simple design, so we won't be using an EEPROM, we'll just be pulling the GPIOs high and low with strapping resistors, and we'll go into more detail later on. But overall, it's actually a fairly simple system and something you can easily implement in your own designs. So let's move over to Altium Designer and check out the schematic before we move on to the PCB design. Here we are now in Altium Designer, and again, all these tips and tricks for making this USB hub can be applied to any ECAD software. I happen to be using Altium Designer, of course. I've put this schematic because it's fairly simple on one single page. This is just a demo project. This is just meant to be a general rough guideline of how to implement a device like this. Of course, this will depend on what your project requirements are, what connectors you use, if it's part of a bigger system, and so on. But take this as a rough starting point. Now we're going into a bit more detail. Zooming into the top left of the schematic, we have our 5V input from the DC barrel jack going into a 3V regulator. I always like to filter my DC power lines, which aren't high-speed digital power lines, with a pi filter. Pi filter because it's the shape of the Greek letter pi. We have C1 and C2 with a series element which is a ferrite bead. Now I'm planning on making a ferrite bead video because that can be a bit more difficult to choose. There are many different things you need to think about when choosing ferrite beads, but just think of this as some sort of low-pass filter for now. Because we're drawing 2.5 amps maximum, or maybe slightly less than that, we want to rate our ferrite bead quite a lot higher than that. I've put 3 amps here, but typically you want to go even higher than that. So you want to choose a fairly chunky series element, because ferrite beads get derated fairly quickly at higher currents. Then we have our 5V filtered, so to speak, and that feeds into a linear regulator. 5V in, 3.3V out, again bypass capacitors C3 and C4, as well as we have this bypass pin here for this specific regulator, and that helps reduce the output noise of this regulator. I like to have a status on LED for these kind of test or demo boards, so this is just a green diode with a current limiting resistor. We can see though that we have this one pin branching off, which is the enable signal to this 3.3V regulator, and that goes off to a net name called VBus Det or VBus Detect. I only want this regulator to turn on once we've plugged in a host, so the hub doesn't turn on beforehand. And we'll see this VBus Detect pin where this comes from in just a second when we look at the USB hub schematic. So let's jump down to this schematic over here. It might look more involved, but it's very, very simple. We have the host micro B connection on the left, we have the USB hub in the middle, and the 4 USB-A ports on the right-hand side for all the device connections. The load switches I've put up above, and we'll look at those at the end. Starting on the left-hand side, we have our host connection, micro B, as I said. Again, you can use any connector, or if it's on a board device, you might not need a connector. You might be just connecting this to a system on chip, microcontroller, or so on. I like to give all of my nets labels, and I think that's good practice because this makes your PCB design life a lot easier, as well as adding flags that this is a differential pair because you want to tell Altium Designer or your ECAD software to route them as differential pairs later on. At the top, we have a pi filter again, capacitor, ferrite bead, capacitor. Even though we're not using this 5V from the host very much, I always think it's good practice to do so. I've added in ESD protection. This USB LC6-2SC6 is a fairly common part. It's a USB high-speed specific TVS diode array. We're protecting the data lines as well as the power line as well. You might also have noticed this shield and ground connection here. And this really depends, and there's quite a big topic of debate. How do you connect your shield? Do you connect your shield ground to system ground? Do you connect it to chassis ground, and so on? And this really depends on the scenario. So I've put the most generic case here where we're simply coupling the shield or chassis ground via a capacitor to our system ground. Now, if you have a fully metallic enclosure, your shield will connect to the chassis ground. In certain cases, you might want to leave your shield floating and so on. It depends on your enclosure, it depends on your specific system. I've just put a fairly generic case here where we're simply having a cap between shield ground and our system ground. Again, it really depends on the scenario. Moving on, looking at the hub IC, we're feeding the host differential pair into a hub. And this is on the left side here. This is our upstream port, so to speak, and the 4 devices are downstream ports, so to speak. We have various power connections. We have VDD 3.3 and VDDA, which is the analog side, 3.3. And the datasheet and the evaluation boards just simply recommend tying this all to 3.3 volts, no additional filtering, and of course 100 nanofarad capacitor per VDD or per power pin, and they've added a 2.2 microfarad capacitor as bulk decoupling. Above these power pins, we have this VBus det or VBus detect pin, which we saw earlier. Because this is a 3.3 volt device, this USB hub, we can't just simply hook up our 5 volts directly to the VBus det pin from our host connection. We're dividing it down via two 100K resistors. Now this signal is also fed to our linear regulator, the 3.3 volts, to turn this on. We have various other filtering parts here, for example the PLL, various filtering circuitry, and this is taken directly from the datasheet, what capacitor values we need and so on. If you think back to the block diagram, we also need a crystal source, and this happens to be a 24 MHz crystal oscillator with this standard circuitry here. So we have load capacitors, a feedback resistor in case we need one. However, the datasheet says for this specific device, it contains an internal 1 mega ohm feedback resistor, so R21 in this case, so I've just put it as a do not place part. The load capacitance, so C28 and the value of C29, depend on the actual crystal chosen. I've put the formula up here. For this particular 24 MHz crystal I've chosen, the crystal capacitance, the load capacitance is 9 picofarad. I'm assuming about 4 picofarads of stray capacitance. You subtract those two numbers, multiply them by 2, which gives us about 10 picofarads for C28 and C29. And this is a fairly typical calculation. Other parts of the circuitry taken directly from the datasheet are, for example, this R bias pin, which is fairly important, which is a bias resistor 12 kilo ohms to ground. Other than that, let's look at those strapping pins now. We have these pins 24, 25, 28, and 22, which have various different names for the same pin. So it could be, for example, a clock pin for an I2C or 2-wire line, and then we have the SDA pin down here. But we also have these config select 0, config select 1, and so on. If you think back to the block diagram, this was this part down here where we can either use an EEPROM or strapping resistors, depending on if you want to change vendor IDs, PIDs, have more specific settings, and so forth. In our case, this is a very simple example. I'm simply using strapping pins, again taking things from the datasheet. And I always like to put comments on the schematic, which you see in this blue text up here, why I've pulled certain pins high and low. It turns out, again from the datasheet, that the config select pins, so cell 0 and cell 1, if we pull them both low, we're using the strapping options. We're setting this hub as a self-powered device because we're using external power. We have individual power switching for the ports. So again, this has to do with the load switching, and individual overcurrent sensing, again, with the load switches. So that's why I've pulled config cell 0 and config cell 1 low with a 100K resistor. You could of course pull them down to ground, just with a short, so to speak, but I always like to place resistors in the way in case I change my mind or I have to adapt something later on. This way I have a pad here, which I can either then, via a little jumper wire, solder over to 3.3 volts, for example. Then we also have these non-REM or non-removable ports, so non-REM 0 and non-REM 1. And it turns out if I pull both of them low, that means all of the ports, the downstream ports, so all of my USB-A females, are removable. And of course this is what I want, because in this case I'm making a USB hub where I can attach and plug in devices as I want, so to speak. Therefore, non-REM 0 and non-REM 1, R18 and R19, are pulling those both low. That's pretty much all we need for our strapping options for this particular configuration, and if we're not using an EEPROM. The EEPROM connections aren't particularly difficult either, and you can check out Microchip's evaluation board if you want to learn more about that. Moving on, we're finally getting to the device or downstream ports of this hub. This means we have all of these differential pairs, so USB-DN, USB-D+, as well as the enable signals for all of our load switches, and our overcurrent sense input pins, again coming from the load switches. Reminding ourselves from the block diagram, this was this section on the right over here, with our load switches, enable and overcurrent signals feeding the USB-A female connectors. So the data connections simply go via ESD protection diodes, again using the same package as with the host connection, to our USB-A female connections. That's all there is to it. Same goes for 1, 2, 3, and 4. The power is not our main 5 volt power because we're taking this through the load switches, which I'm showing you in just a second. Again, pi filter, and you can see we have these fairly large capacitances now directly at the power pins of this USB-A female connector, 100 microfarads. This hub will then act as a host, so to speak, or an extension of the host. We want to be able to supply 500 milliamps, also with a large bulk decoupling capacitor, as dictated by the USB standard. So our load switches are up here, there's 4 of them, 1 for each device connection. We're taking our 5 volts filtered from the load switch, bypass caps C6 and C7 in this case, as directed by the datasheet of this load switch. We have our enable signal, which is logic high, and we have our end fault signal, which is essentially a fault condition or an overcurrent condition signal. Now this signal for this particular IC, this MIC2099, is open drain, so it would require a pull-up resistor, which I've put here as a do not place. The reason I put a do not place here is because this overcurrent signal feeds into the overcurrent input pin of the USB hub IC. Now it turns out that this overcurrent signal pin contains internal pull-ups to 3.3 volts, therefore we can omit these resistors. The reason I put them as do not place for a demo board, I always think that's a good idea in case you've misread something or similar. On the side we have our output, which then goes to the ports, and once the output is on, I like to indicate that with an LED, for example on this demo board. Again, green diode, current limiting resistor. The last pin we haven't looked at is this I limit pin, and as the name suggests, the value of this resistor will change the maximum current that this IC, this load switch will supply before giving an end fault condition or before clamping the current. From the datasheet of this particular device, very easy to find that for 330 ohm resistor approximately, we get a current limit of about 450 to 750 milliamps. And of course there's going to be variations within these ICs, but it's around the 500 milliamps we want. So this part of the schematic is duplicated 4 times, and the output power is then connected through a pipe filter again to the USB-A connections. And that's all there pretty much is to it. Let's now talk about the PCB design aspects when you're implementing a USB hub IC such as this one. I've made a very simple demo board. This is 4 layers, and I'd recommend going with at least 4 layers for a design like this, and 4 layers is sufficient. Of course, depends on your other peripherals you have on your PCB as well. But for this, just making a simple breakout board for this, where I have a host connection, and then 4 device connections on the right-hand side. 4 layers is what I'd want. 2 layers, it'll be difficult to meet the controlled impedance requirements as well. And 4 layers, because of the smaller spacing between layers 1 and 2 and layers 3 and 4, we get better EMI and SI performance as well. A brief overview of the board. We have the majority of the components mounted on the top side, although I do have some capacitors under this QFN, which is this quad flat no lead package of the USB hub IC, which is the center here. We have some decoupling capacitors mounted on the bottom side, and I'll show you why later on. It is possible to put them on the top side, however that makes routing out all of these parts and all of these traces a lot more difficult. For this fairly quick demonstration board, this made my life a bit easier. We have our centerpiece, which is our USB hub, the USB 2514 by microchip, connected to a host with ESD protection, some filtering. With a crystal over here, we have the power section, our 5V input, DC barrel jack on the bottom left, feeding through a pipe filter into our LDO regulator. And out of this USB hub, we have then 4 data connections to ports 1, 2, 3, and 4. Again, ESD protection on each, load switches, as well as quite a lot of bypass capacitance, 100 microfarads each on the power lines after the load switches. So let's go through in more detail after this overview. If we go to Design, Layer Stack Manager, we can look at the stack up of this PCB. So how this PCB is built up and what layers I'm using. My favorite and my preferred 4-layer stack up is have layer 1 signal with routed power. In this case, routed power is completely fine. My first internal layer is ground. Then we have a thick core material. Then the third copper layer or the second inner layer is ground again. And the bottom layer is signal again with routed power. This stack up I got from the PCB website for the stack up or the standard stack ups for multi-layer PCBs. And of course, this will depend where you get this manufactured. The stack up is important because we'll need this for our controlled impedance traces, and we'll talk about that in just a second. In essence, for a 1.6mm PCB, all I did was copy this information. So copper thicknesses, pre-baked thicknesses and types, including the dielectric constants and so on. So all this information just transferred over like so. The nice thing about Altium Designer is, even though of course you could use other tools, other impedance calculators, is that the impedance calculator, once you've entered your stack up information here, I can go to the bottom tab, click on impedance, and then I can add various different impedance profiles, and Altium Designer includes a 2D field solver which calculates the required trace widths or impedances. All of my signal lines I typically like to route as 50 ohm controlled impedance, unless they need to be specified otherwise. So that's my first unit I have here. So single-ended 50 ohms, and it turns out for this stack up I need about 0.17 millimeters to give myself 50 ohms single-ended. However, for the USB differential pairs, of course I need a differential controlled impedance, and the USB standard indicates that there should be 90 ohms differential and 50 ohms single-ended. The single-ended impedance we can get, of course, from our single-ended 50, so that sets the trace width. So I've set that to 0.17 to give myself 50 ohms single-ended, but then the differential impedance is determined secondly by the trace gap. So I've played around with the trace gap to give myself an impedance of about 90 ohms. Of course, this will vary with manufacturing tolerances, weave, and so on, but USB 2.0 isn't that particularly fast. So as long as you're around 90 ohms, this will work. So trace width 0.7 millimeters to give myself 50 ohms single-ended, and 0.22 millimeters trace gap, so the spacing between the positive part and the negative part of my differential pair is 0.22 millimeters, which gives me 90 ohms differential impedance. I can use this then by going to the design rules, then going to the differential pair routing and saying for any differential pair, because I only have USB differential pairs in this design, I want to use my impedance profile, which is Diff 90. Therefore, all of my traces you see here are routed with 0.71 millimeter tracks and a spacing of 0.22 millimeters. So now let's look at how I actually routed these differential pairs, given that we've now calculated our controlled impedance. We start on our host connector on the left-hand side. This is on the top layer, our micro B connector. Notice that for micro B connectors, you should leave a bit of an overhang because we have this lip typically which needs to go over the board edge. So I space this a tiny bit outside, making sure I have enough clearance between this pad and the board edge. 0.4 millimeters at least is usually what I go for. In any case, we have the positive and negative part of this differential pair. We route out straight into the ESD protection, and this is what should come first. You can see I had to branch out to get into these pads, but this is completely fine. This is a very small and short impedance discontinuity, will not cause any problems at all. On the other side of this ESD protection, I route out, down, and into the host connection of my USB hub IC over here. You can see this little squiggle I have here, and this is for intra-pair differential length matching. We need to match between the positive and negative part of a differential pair. We should try and match these lengths or these times or delay times as close as possible. In Altium Designer on the bottom left, if I click on the PCB panel, then scroll down to USB host, DN and DP, I can highlight these connections, and we can see because of this little squiggle I've added on one line, I've matched the delay on the right side here, both to about 114 picoseconds. Generally, with differential pairs, I try to match within 5 picoseconds, depending on the protocol, of course. Now, the matching between differential pairs, for example, between the host differential pair or any of these devices, of course, does not matter. The most important thing here is that we match within, so intra-pair differential skew matching. On the other side of this USB QFN or USB hub, I have my various ports. I route out, and I try to keep clearance between sensitive signals or between other signals. So I could also route my differential pairs like so, very close together, but then you get crosstalk, you get coupling between these signals. If you have the space, of course, try and use it, space out as soon as you can. And for each device port, I route again into the ESD protection, out, very small distance between the ESD protection and the connector, as it should be. And we can see that in 3D, we have the connector straight into the ESD protection, differential pair into the USB hub. That's all there is to it. Keep in mind, however, we don't need to just think about the forward path, we also need to think about the return path. Layer 2 underneath should be a solid, continuous ground plane. That's why I have below layer 1, one dielectric spacer where I've got a solid return plane. And as you can see, all the differential pair signals and any I/O signal is routed directly above a ground plane or suitable reference plane. The other I/O signals, for example, the USB port power, so for controlling the load switches, aren't that critical. I try to route out, give myself some spacing, again between I/O lines, even though these might be a DC, I always try to space out my lines if I have the space. What you can also see is when I'm using vias to drop down to the bottom layer and then route along, I'm also dropping ground vias. You don't have to just think about the ground or the return path on a 2D plane, but what happens if you're switching from the first reference plane to the second reference plane? On layer 1, we're routing signals here, we're referencing layer 2, but on layer 4, we're referencing layer 3. To help this Z-axis or this third dimension transition, I place what's known as a transfer via close to any signal via. Of course, in more dense designs, this becomes harder and harder to do, but you can group, for example, several of these signal vias with one transfer via, one grounded via, so to speak. The USB hub, the remaining parts are simply the strapping resistors. I have short connections to my strapping pin. These aren't particularly critical. What is critical, however, is my bias resistor, which I try to place fairly close to this IC. As well as this crystal connection over here. In 3D, we're coming out as these input and output lines, our feedback resistor, which is typically a do not place. Then we have our load capacitors routing in to our crystal. Now this could be further away, that would be fine, but I try to keep my crystal and load caps fairly close to the relevant IC. I don't really like the package pinout because we have the host differential pair pins right next to the crystal pins. That's why as soon as we come out or in to this package with the differential pair pins, I want to space these away from these sensitive crystal traces. So try to give yourself maximum space, given this not ideal pin out. Now we've looked at I/O traces, we of course need to think about decoupling of this IC. And as I said before, I've placed all of my decoupling capacitors, on the bottom of this IC. And this is typically what I like to do with QFNs, even though this means double-sided assembly. I predominantly do this because this gives me more routing space because I have to fan out this fairly fine-pitched QFN. This QFN has a pitch of about 0.5 millimeters, and I want to make my life a bit easier. That's why I can place the decoupling capacitors on the bottom side, and this is perfectly fine for such a comparatively slow system. So I take, for example, a power pin or one of these filter pins, very short and wide trace, directly into a via. On the bottom side, I come out of the via, wide trace, decoupling capacitor, and then I use, as my return connections, so my ground vias, I use the ground vias which are part of the QFN package, trying to keep my loop areas as small as I can, given the double-sided placement. So short connection, via, short and wide connection to the out of the coupling capacitor, ground connections directly to the QFN grounds. And that's my preferred way of routing out QFNs, if I can do double-sided assembly. When it comes to power routing, from the DC barrel jack, and I'm routing power because this is a fairly low speed design, even though it's USB high speed, we don't have particularly fast edge rates, and routed power for this is completely fine. I've done this many times using this particular IC. I'm using power traces of about 0.7 millimeter width, and this is because we want to carry a fairly considerable amount of current, in certain places 2.5 amps, especially this main 5 volt trace here going along this is carrying all 2.5 amps approximately. Therefore I used, as usual, the Saturn PCB design toolkit, which is free to download. I've used the conductor properties tab, typed in a conductor width of 0.7 millimeters, a temperature rise of 30 degrees. I click solve. We can see this trace can carry 2.5 amps for 30-degree temperature rise, which I think is fairly reasonable. Given also this is the completely maximum load this would ever see. Therefore, all routed power, and I did my routing of the power last, a lot of it on the bottom side of this PCB, all at 0.7 millimeter trace width. The traces, which then go to the individual devices, of course I can make thinner because each individual device only draws up to about 500 milliamps of current, so therefore I went with about 0.5 millimeters. The remaining connections aren't that critical. We have our load switches. I try to place my bypass or decoupling capacitors close to the relevant power pins with short and wide traces. Anytime I drop a via to ground or power, I try to keep my trace short and wide as possible, but of course my via not too close to the pad because that might cause solder wicking and assembly manufacturing problems. So short wide trace out a bit, drop the via down to a ground power plane. Then my power routes through this pipe filter with this large decoupling or bypass capacitor into the power pin with my USB-A connections. And I've just simply repeated that circuitry for all of these 4 device connections. So there's not actually too much to it. The main points being the controlled impedance differential pairs, matching intra-pair spacing, ESD protection close to connectors, routing power with fairly wide traces, using solid continuous ground planes, and the usual PCB design aspects or best practices that you should always adhere to. You can also see I filled in the top and bottom layers with a solid copper pore, and this is connected to the ground net. Because I have then ground copper pores on layer 1, layer 2, layer 3, and layer 4, we can see all of these vias are stitching vias. I want all my planes connected together to give me the lowest inductance return path and connections. I simply went to Tools, Via Stitching, Via Shielding, and added stitching to a net, in this case the ground net, to tie them all together automatically. For the sake of completeness, even though this is just a USB demo board, I've added some mounting holes in suitable positions, and these are grounded. I've added some silkscreen indicating what all these connections do, what port numbers they have, revision numbers, my initials, my logo, and so on. It's always good to add this information to your silkscreen to help the end user out, or to help out during debugging. Other than that, the shield connections, I've simply used wide traces. Again, this is a very generic guideline and I plan on making a video on grounding and shielding, but for this I've just used a single capacitor to ground, as we saw in the schematic. Just as a simple test, here's this USB hub as a test I designed about 2 years ago, again with micro USB connector. I'm going to hook this up to my computer. First of all, let's look at the device manager. We can see I have a couple of hubs already connected, but now let me just connect this hub. So now it's on and connected to my computer, and we can see a third hub has appeared. So now we can test it by connecting, for example, a dongle, for example, my wireless mouse and keyboard. So I'll take it out of my computer, and then I can plug this into any port I want. For example, I'll just use the first port over here. And now I can move, for example, my mouse, again, connected through this USB hub, just to show that this simple configuration does actually work.